Alright, today is our first video on waves. Doing the wave there. Specifically mechanical waves. We're already going to talk about all kinds of waves, but specifically mechanical waves, meaning we can see something moving. There's actually particles that are actually vibrating that we can view. Okay? Alrighty. So mainly looking at mechanical waves, but we're going to look at all kinds of waves because it turns out waves have specific properties that all waves have. So waves are a little different than what we've studied so far in that waves, the energy can move, but the particles don't have to move from point A to point B to transfer energy. Like we learned out kinetic energy of your car, you could drive from one place to another and the energy can be transferred to another place where your car's going by moving the actual mass. Well, in this case, we're sending energy, but the particles can vibrate and they can move, but it's the wave energy that goes from point A to point B, not the actual particles. So with all waves, energy is moving. Both mechanical wave parts are actually moving, like atoms and so forth. Okay, so here are a lot of different kinds of waves. We've seen ocean waves and some kind of artsy type wave and a black hole. So we're going to talk about gravity waves, but gravity waves would not be a mechanical wave because it's vibrating space and time, but we still wouldn't call that a mechanical wave. This is looking at radio waves from outer space. Now that's electromagnetic radiation, not a mechanical wave. But it turns out all waves have the same property, so we're studying the same thing. Okay? So what are mechanical waves? What do you think they carry? Can you see waves? There are all kinds of examples. Well, you should have already looked at some examples, some FET examples that I gave you. One was you're shaking a little chain-like thing and find out what factors affect the speed of the wave on that thing. And you also did some drippity drops on some water. You looked at a FET, we dropped some water and looked at the waves, and you changed some frequency of the drops and some amplitude, and you also converted to sound, and you've also looked at the light version. Turns out light is not a mechanical wave because you're not actually when light travels through the air, it's not vibrating the air. It's actually a vibrating electrical and magnetic field is what that is, but more on that later. Okay, mechanical waves. So any kind of disturbance you have, and this disturbance carries energy from one place to another. Like I walk across the floor, and other people can feel me walking across the floor, because every time my foot hits the ground, it squishes the particles, and those particles pull on the particles next to them. Those particles pull on the particles next to them, and it travels across the floor. It's a mechanical wave traveling through the floor. But it requires some kind of a matter. Okay, so mechanical waves always have to have a matter. You can't have mechanical waves travel through the vacuum of space because there's nothing to vibrate. There's nothing mechanical there. Light can propagate through that, but not a mechanical wave. Even sound, we're going to find out, is a mechanical wave. Sound doesn't propagate through space because you have to vibrate something. Right now I'm vibrating the air. My vocal cords are squeezing the air, then they're unsquishing the air. They're squeezing the air, then they're unsquishing the air. But without that air, there's nothing to transfer that, and you couldn't hear a sound. So the medium is what the wave travels through. You may have maybe looked at some psychic things before. So if you want to talk to the other world, beyond life, you have to have a medium. And that medium is the person that can talk to the dead. Without that medium, you can't communicate with the dead. So medium is kind of what you're kind of the go-between. So for waves, a medium is what it's traveling on. It's the solid, liquid, or a gas, okay, that travels through. Okay, so without a medium, you can't propagate or have a wave transfer anywhere. Okay, so how do you create them? So I already simulated some earlier. Me walking across the floor makes mechanical waves. So all you do is source of energy. That, in my case, it's me walking across the floor. So that energy causes a vibration through which it travels through the medium. So we have vibrations that travel through the earth all the time. We can look at what happens other places. We know when other countries blow up bombs because we're looking at vibrations in the earth. And because we have them at different places, we can actually find out exactly where that vibration came from, whether it's an earthquake or a bomb or whatever. Okay, so types of mechanical waves. One is a transverse. Transverse is a one that travels, the vibration goes transverse or across the direction of the wave. So you notice the only thing this particle does is go up and down. This particle only goes up and down, but the wave goes perpendicular 90 degrees to that. It's called a transverse wave. So a few terms, how we measure transverse wave. The amplitude is from the center to the top. There is something called a peak-to-peak amplitude. Sometimes we use in electricity for measuring like a potential or something, or voltage. But whenever we talk about amplitude, it's always from the center, non-disturbance, to the top. Negative amplitude would be to the trough down here. So that's the peak and that's the trough, and the wavelength is from the same to same. That's one wavelength. Or I could start here, that's half a wavelength. As I'm going up, I have to be going up over here. So that's one whole wavelength. So it's from same point to same point. I could start here, then one whole wave would be, since I'm coming down here, I have to be coming down here, that would be one whole wavelength. It's the same everywhere on here. This is just the easy place to measure a wavelength. Okay? Direction of propagation, that's the direction the wave travels. Okay? There's the crest. There's the trough, fancy names. Wavelength, we're out of American letters, so we're going Greek here. So we're using the lambda for a length here, the wavelength. The amplitude is simply from the center to the top, okay, which is the same as this down over here. It's just the negative amplitude. And this is the equilibrium position, okay? So those are your parts. Know it. Alrighty, so we have more than just a transverse wave. Transverse wave is the shaking up and down. If you had a slinky, that would be great. It's awesome. You can make these waves pretty easily. The shake is this way. So you squish it, and it goes that way, bounces off the back, comes back. And you squish it, it bounces off this side and comes right back. So a tuning fork would be an example of a longitudinal wave because it squishes the air and it unsquishes. Actually, I did it just backwards with my hands. So that would be the squish of the air, and that would be the unsquish. So this would be the high pressure it makes, the squishing together, the compression, and then when they go the other direction, it's called the rarefaction, or the spreading out of the air. So that's called a longitudinal wave because you notice it pushes this way, and it goes along the same direction as what the wave is traveling. Turns out sound is a longitudinal wave. This is exactly what my vocal cords are doing right now. They're vibrating, squishing, and unsquishing the air, squishing and unsquishing the air. I'm making a longitudinal vibration that the microphone is picking up. Okay, so this is the compression is right over here. The squish, that's the high pressure. That's the high pressure, the squishing of the air, and this is the low pressure over here. Same thing happens on the slinky, called the rarefaction over here, but the compression is over here, and it's going in the same direction as what the vibration is in. And wavelength is from same to same, from maximum rarefaction to maximum rarefaction, which is tricky to measure to find that point. A little easier normally to measure the center of the compression here to the center of a compression. Easier to measure the wavelength. Okay, so basically the vibration is going, but we're going to see in a moment the particles really don't travel anywhere. Okay, so the transverse, the source of the wave, it goes up and down, vertical to the direction of the transport of the energy, whereas longitudinal, it travels in the same or opposite direction as the vibration. Okay, in an earthquake, we tend to make both of these. This can be as go along the top. You can even sometimes feel that the earth actually goes up and down a little bit. And some of the part of the vibration of the earth is just a squish and then unsquish. Alrighty, now this is a little bit trippy if you focus on this. It looks like particles are traveling. Look at this, we're following a wave. Maybe if this is a surf is up, you go, hey, I'm surfing, dude. But if you actually take a look at a single particle, back and forth, it doesn't actually go anywhere. Pick another particle, any particle, doesn't matter which one you pick. It actually goes back and forth, back and forth. They're not going anywhere. The particles look like they're moving, they're not. The wave energy is moving, the particles are just going back and forth, back and forth, back and forth. It's the wave energy moves, even transversely down here. You can see this more easily. They're just going up and down, up and down, up and down. The wave energy goes back and forth transversely to the direction of vibration, but the particles simply just move up and down. They're not actually going anywhere. No net displacement. Okay? So wavelength is from same to same, whether it's trough to trough, compression to the compression. That's the wavelength. Okay, which would be the same over here from this point to this point, or from this point to this point. It's the exact same length. Or from the middle of this to the middle of this, it's all the same wavelength. All right, so what happens, what's an ocean wave? Turns out this ocean wave is actually a combo. It's not only a transverse, it's also a longitudinal. So what's it going to look like if to the water then? If it's both transverse up and down and sideways, this vibration of the water, how does that look? Well, it's called a surface wave. So a surface wave is traveling across the top. It's not only vibrating transversely, but also longitudinally. Okay, let's take a look here. So if you look at this as a bobber in the ocean, if you're out in the middle of the ocean, not where the water breaks, because what happens in an ocean wave as the ocean gets less deep, it gets more shallow, it starts to drag. This wave starts to drag on the bottom. It slows down on the bottom and starts to topple over. That's what a surfer tries to catch. But a surfer goes out before it breaks, before the waves even break. This is all that happens. It's not that exciting. All a surfer does is go in a circle, because you have the longitudinal portion back and forth as well as the vertical portion up and down. And as you go lower, look at this, there's not as much displacement. You go clear into the water, you don't even hardly do anything. So if you're scuba diving or swimming down here, you don't even notice that there are waves until you get to the top. As soon as you get to the top, then you start doing this on top of the ocean, going up and down, up and down. Okay? Called a surface wave. It's a combo of both. Alrighty, so now we have some other terms. Period is the time it takes to make one wave. It's the big T. It's the time for one event. Like the period of one class is a time for one event. Time to make one wave, either longitudinal or transverse or surface. And seconds is, of course, the term we use to measure that. Frequency is the inverse. It turns out it's 1 over the period. So period is the time per event. Frequency are the events per time. It's how many cycles per that time. They're the inverse. And it's a new unit called hertz, which are events per time, or seconds to the -1 would be what a hertz would be. So frequency and period are the inverse. Period is the time per event. Time per events. Frequency are the events per time. Okay? Alrighty. Now to find the speed of a wave. Okay? Well, you just do a distance per time. You should have already practiced this in the simulations before you got to this point. You measure distance per time. But an easy way to measure a distance is by the wavelength. So you could stop, go back to your simulations. You could stop the simulation and just measure the wavelength from same to same. Then all you have to know is the time to make one of these. How long does it take for one full wave to pass? And that would be the speed. But since period is the inverse of frequency, we can substitute that in, and now it's actually times that. So now it's a wavelength, your distance per cycle, times your cycles per second. That is how you get your meters per second. So this is called our wave equation, and this is what we're going to frequently use in this unit to find the speed of the wave. Okay? Alrighty. So speed of the wave. Here's what you should have found out so far. That the speed of the wave, you can't change it unless you physically change the medium. You change the tension, you change, so it's a whole different medium altogether. The speed should have been constant for all your trials. You increase the frequency, it makes the period shorter, and it makes the wavelength shorter, but it actually doesn't change the speed. Let's go back a little bit. Okay? So what happens is, the higher the frequency, what that means is the shorter the wavelength, the smaller the wavelength is. Or the longer the wavelength, the lower the frequency. They're the inverse of each other. It doesn't change the actual speed of the wave. The only way to change the speed of the wave is to change the medium. Whenever you go from one medium to another, the speed will change. Okay? So that means the speed of a wave is a constant in the medium. Speed of sound right now, it's a constant. It's about 340, maybe 6 meters per second traveling through the house right now. And as long as it's all the same temperature everywhere in the house, it's all the same speed because it's the same medium. But if you change the medium, like by changing the temperature of the air, the speed actually can change. But if you don't change the medium, it's going to be a constant. Okay, so the wavelength is inversely proportional to the frequency. Alrighty, we're going to have to pause. We're going to do a couple quick problems here. So a wave in a spring has a wavelength of 0.1 and the period is 0.2 seconds. What do? We just divide. It's the distance divided by the time, 0.5 meters per second. Okay, one more problem. Wavelength is, I don't have it, but it's going 4.4 meters per second, and the frequency is 2. Dios mío, how do you find your wavelength? Solve for the wavelength. Solve for the wavelength, and you end up with a 0.2 meters. Okay, so next is wave behavior, but this is your introductions to waves.